Welcome back. This is the second in the series of thermodynamic slides for my Chem 112 class. Just like we had chemical equations, we have thermochemical equations. Basically what those are the same exact thing that we've seen before. We just add some type of notation for the energy. Okay, and so we can write the energy, the amount of energy, as a product or a reactant when we write that in the chemical equation. And here I'm showing it as a product. But if I wrote it on this side, then it would be a reactant. And so that's just another way of telling you, is it an endothermic or exothermic? Obviously, if it's a product, I'm giving off heat, so it's exothermic. If it was one of the reactants, I was putting it into the reaction, then it would be an endothermic reaction. And just like that, I also can just write the delta H as either a plus or a minus value. Now, it's important when we're looking at thermochemical equations that we remember that what we're looking at here, this is 1 because we are lazy chemists and so we don't write the ones. But these coefficients at the beginning are how many moles of the substance. That's very important. And so how many moles we're looking at, or if we're looking at just gases, sometimes we consider that atmospheres. But it's important that we define that as moles as we're going through these thermochemical equations. So just keep that in mind. The chemical equation, just like I said, wrote it as a product in the previous, or I can notate it as the delta H of the reaction is a negative 3523. That's also telling you that that is heat that is given off. Okay, heat's given off, removed from the system, so it's a negative value. Just another way of writing it. And of course, if that is negative, less than 0, it's exo. And if it's greater than 0, it's endo. And I've said that a few times because I want to make sure that you remember it. Okay, so let's write a thermochemical equation. Now, this says example 15.2. And 15.2 was that calorimetry problem that we worked that had the acetic acid in it. Let's see. I'm going to go back to it just a minute. All right, so yeah, it had acetic acid. So CH3COOH plus sodium hydroxide gave us sodium acetate and water. All right, and so water when it's formed is usually a liquid. This was aqueous, however you want to say it, and these were aqueous. Okay, all right, and so that means they're dissolved in water if you don't remember that. Okay, now what else do I need to be able to write on here for it to actually be that thermochemical equation? And that is, I need to what? I need to add the energy. And so the energy for this particular equation was a negative 56.8 kilojoules per mole. All right, now remember, so let me write it all on one so it'll be a little bit neater for you so you can see. All right, so CH3COOH aqueous plus sodium hydroxide gives me sodium acetate plus water plus, since it's negative, I could have written it as plus 56.8 kilojoules per mole. How come I can do that? Because it's a product, so it's saying it's evolved. Or I could write it as the delta H equals the minus 56.8. Either way you see that, those are exothermic. I either tell you with the sign or I tell you that it's a product, not a reactant. Okay, so standard states. You remember this hopefully from your Chem 111 days, because in a standard state, that is the most stable state of a substance at 1 atmosphere pressure and 25 degrees C, or otherwise known as 298 K. And those are defined because remember, those simplify our math when we're working a lot of problems. I've given you, or made available to you, Appendix K. Appendix K for your standard states, solid, liquid, and gas. And the values of the delta H0. Okay, and the delta H0 is your standard enthalpy. Okay, your standard enthalpy for different compounds. And so you're going to use that information from Appendix K to work a lot of these problems. One thing you'll notice in Chem 112 that we do use a lot of tables and standards and constants and things like that because of the math that we're doing. All right, so for gases, just like remember that we have moles for liquids, and then we have gases are going to be atmospheres. So for gases, the standard state is 1 atmosphere. For aqueous solutions, the standard state is always going to be a 1 molar solution. Remember what 1 molar means? M is the same thing as what? Moles over liters. Moles of solute per liter of solution. That's important because remember, you get stuck on some of these calculations if you forget that. So the standard molar enthalpies of formation are basically how much energy changes, either put in or evolved, for one of the substances that's formed from elements. Okay, now you put things together and you make something else in a chemical reaction, basically. So, you know, if I have A plus B gives me AB. All right, so I had two things that were separate alone, and then I bonded them together somehow and created a new molecule. If these are elements, or if they're in their elemental form, then their molar enthalpy of formation is 0. Okay, now if it's copper, okay, or iron, okay, like a metal, whatever, they're 0. Also, if it's how it normally occurs in nature, like O2, that's also 0 because that's its elemental form. We're going to use something called Hess's law. Hess's law looks really crazy when you first look at it, but it's really not. It's very simple. It's telling us here that the change in enthalpy, the standard molar enthalpy of change for a reaction, is the sum of all, N means ever how many you got, the delta H0 F of your products, so this is the formation, the standard molar enthalpy of formation for each one of the things that are produced times their coefficients, minus the sum of all the things that are reacting times their coefficient. Okay, what the heck does she mean? Well, one thing she means is make sure that you have a balanced chemical equation when you do these, because if you don't, you're gonna not be doing the correct thing. All right, so let's do an example. Calculate the enthalpy change, so that's what we're looking for the reaction of 1 mole of hydrogen with 1 mole of fluorine to form 2 moles of hydrofluoric gas at, this is critical, 25 degrees C and 1 atmosphere. 25 degrees C and 1 atmosphere tells us what? That is standard state. Yay. Okay. So that simplifies our math, which you know I'm always happy to have my math simplified. All right, so the first thing we need to do is what? first thing we need to do is balanced chemical equation. All right, I'll go back to it so we can remind ourselves. So we've got H2 plus F2 is going to give us HF, and these are all gases. Now, H2F2 as a gas, that is their what? That's their standard state already. That's their elemental configuration. So Hess's law tells us that the delta H of formation is going to be equal to the products minus the reactants. You're going to see that in a lot of problems this semester. Okay, so we have to do what? We have to know what the delta H, and you'll see it like delta H 0F 298, stuff like that. 298 is what the Kelvin is, so you know that that is the standard. If you look this one up, it's minus 271 kilojoules. You've got to watch those units because if I get too close to that side, it goes forward on me too. All right, so the delta H of HF when I look that up on Appendix K, go ahead and do it now so you know how to do it, is minus 271 kilojoules. Okay, now it's helpful to go ahead and kind of make up a little table of what these are. So this one is the minus 271 kilojoules. These are 0, right? Because they're in their elemental state. So, but make sure that I've done what to this reaction? Balanced it. Okay, is it balanced? No. Okay, in order for this to be balanced, I'm going to have to put a 2 there. When I put the 2 there, then it's balanced. 2 and 2, 2 and 2. Okay, so so remember why this is important, because I've got to multiply the coefficient by the standard molar enthalpy. So the delta H F0 is going to be equal to the products, which is the minus 271 kilojoules, but it's what? Times 2 minus 0 plus 0. Okay? So that really doesn't bother anything. And a lot of times when I go through and I do this, I'll just go ahead and mark them out because I don't even put it in there. All right. So then that means that our delta HF0 is going to be equal to minus 271 times 2 kilojoules per mole. Sorry, that's molar. So that gives us a negative 542 kilojoules. Why is it just kilojoules here? Because this is really 2 what? Moles. It's 2 moles times kilojoules over moles, so it gives us kilojoules. So that is the enthalpy change for the reaction of hydrogen gas and fluorine gas producing hydrofluoric acid gas, or hydrogen fluoride as it's known. Okay, calculate the enthalpy change for a reaction in which 15 grams of aluminum reacts with oxygen to form aluminum oxide at 25 degrees C and 1 atmosphere. Again, what did it tell us? Yay, that's standard state. Look for that, because once it does that, then it'll make not just what we're doing now, but what things that we're doing later a lot easier as well. Okay, so first thing we got to do is what? Balanced equation. All right, so it's reacting aluminum, and most of us know aluminum is Al plus oxygen, and it's going to give us, they tell us what this one is, Al2O3, so we don't have to worry about putting that together. All right, so aluminum is a regular metal, right? But we are going to have to balance this equation. So I've got 2 aluminums, so I need 2 aluminums over here, right? And then, I got 3 oxygens over here and 2 over there. Now, normally what I have to do is I'm going to make those common denominators. So I do a 2 here and a 3 there. That gives me 6 oxygens on both sides. So that one will have to be a 4. If you don't remember how to do this, you need to go back and review how to balance an equation. Okay? Or you can sit down with me, make an appointment, or during our study session, our review session for the test or whatever, or after lab, use your time wisely. Then we can review that for you if you need it, because this is critical. You got to remember how to do this. Okay, now we're going to use Appendix K, and we're interested in the product. Okay, we're interested in the product. So because we're interested in forming something. So the formation of Al2O3 is what we're doing. So that's the enthalpy of formation that we're interested in. Okay, so we can look on Appendix K, and when we do that, we're going to see that the delta H0F of Al2O3 is going to be a negative 1676 kilojoule per mole. That pen's driving me crazy. Okay, 1676 kilojoule per mole. Negative. It's hard to see it because my pen's trying to mark everything out. Okay, so we have that. That is for this, right? That's for the aluminum oxide. So what we want to know is, what is the standard molar enthalpy of formation? Now, it didn't tell me how many moles. I know the reaction and how it should go, but it didn't tell me how many moles of this I have. What it did was it told me how many grams of aluminum I have. Now, as very mature chemistry students, we know that we can convert grams to moles. And even though I'm looking for this, I can use my balanced chemical equation to go from grams of aluminum to moles of aluminum oxide, which is what I have to do in this so I can get this actually calculated correctly. So the first thing I'm going to have to do, if I'm looking at kilojoules eventually, I'm going to have to know moles, and then, because this is kilojoules over moles, right? So it's moles times kilojoules over moles is going to give me kilojoules, enthalpy change. All right, so kilojoules is going to be equal to, how do I get from grams to moles? Well, I've got 15 grams of aluminum, and if I look at my handy-dandy periodic table that I've provided you a copy of, you will see that there are about 27 grams of aluminum in 1 mole of aluminum. Okay, that gives me moles of aluminum because those cancel. Now, that's all well and good, but my enthalpy number is for aluminum oxide, so I've got to go from moles of aluminum to moles of aluminum oxide. In order to do that, I have to look at the molar ratio between aluminum and aluminum hydroxide, aluminum oxide, sorry. So I know moles of aluminum will have to go down here. There are 4 of those for every 2 moles of Al2O3. That will then get me to moles of Al2O3. Moles of Al2O3 times my standard molar enthalpy, which is minus 1676 kilojoules per mole of Al2O3, which is then going to be a calculation. And when I multiply everything on the top and divide by everything on the bottom here, I should come up with a negative 4 negative 466 kilojoules. So the only difference in this one is I was given the grams, and so I had to use stoichiometry and the molar ratio to get me to moles of aluminum oxide, so I could then plug that in. Okay, so that's standard molar enthalpy of formation. I'm interested in products because I'm forming something. All right, so let's look at this reaction here. Okay, this is propane, and we're going to take propane and we're going to react that with 5 moles of oxygen and produce 3 moles of carbon dioxide and 4 moles of water. This is combustion. Okay, I'm burning it. So if you had to predict if this was going to be exothermic or endothermic, what would you think? Is it going to give off heat when you burn something? Yeah, it is. Okay, so most combustions are going to be exothermic, and some are very exothermic, and some are just a little exothermic. Okay, so we are going to look up in Appendix K 2 things this time. Well, actually even more than that, because we need to account for all of the delta H zeros, okay, because we have things that aren't just going to be 0 this time. Okay, so when I look that up, I'm going to go to Appendix K, which you should have printed off. If you don't have a copy, you need to get one because you're going to use it a lot. Okay, Appendix K. So we need to look up the number for C3H8 and CO2 and water. Why am I not interested in oxygen? Because it's an element, so it's going to be 0. Okay, so I'm not going to worry about that one. Okay, so the delta H 0 for the reaction is going to be the sum. This is Hess's law, right? So it's the sum of the products minus the sum of the reactants. So the delta H for the reaction is going to be the sum of all, remember that crazy looking thing, the delta H's of the products minus the sum of all of the delta H zeros of the reactants. But the only other thing is you've got to have what? The coefficients. Remember that one's a 1. Okay, so we look up in Appendix K. Now put me on pause and look these numbers up, because if you don't practice looking the numbers up, then when it gets time for you to do it, you're going to be in trouble. Okay, so put me on pause and go do it. You should be coming back, or you're just sitting there not doing what I say. Minus 103.8, and these are all going to be in kilojoules. The CO2 is a minus 393.5 kilojoules, and water is minus 285.8 kilojoules. Okay, so those are our numbers. So once you've looked it up in Appendix K, it's just an easy plug-in. Okay, so the delta H reaction is going to equal your products. Okay, so we've got 3 CO2s, so we're going to have 3 times a negative 393.5 plus 4 times a negative 285.8. Okay, then that's going to be minus, because it's the difference between those and the reactants. Remember, the oxygen is 0, so it's just going to be 1 times the negative 103.8. Okay, and remember those are all kilojoules. So when we do the math, we're going to have a delta H reaction is going to equal approximately, and I'm rounding, okay, approximately 2220. I got 2219.9, so I'm saying 2220 kilojoules. Okay, now what's the sign on it? Okay, so these were negative. So this was 3 times this number and 4 times that number added together. They were both negative. And then minus a negative number, so you added that. So let me just kind of drop this down a little bit. The 3 times a minus 393.5. Okay, that was, so I'm just going to take this down here for a minute, is a negative 1180.5 plus 4 times a negative 285.8 is a negative 1143.2, okay, and then minus a negative 10, I always run out of room, 103.8 minus a negative 103.8. Okay, so I've got negative, negative, and then minus a negative. And minus a negative is the same thing as what? Adding it. Okay, so I've got minus 1180.5 plus a negative 11432. So you add them together, they're going to be a pretty big number. A negative number, okay, and then plus 103.8. So that's where this comes from, and its sign is what? Negative. Negative, negative, negative. All right, so that negative number tells me what? Actually verifies my original hypothesis that it's going to be what? Exothermic. Yep, it's going to be exothermic because I'm giving off heat. I know that because I have a negative delta H, right? Very good. If I add just a little algebra to this, okay, because so far really all I've been doing is adding some stuff together. I mean, I had to multiply a little bit, but adding some stuff together. If I add a little bit of algebra and our knowledge of how algebra works, we can actually solve for one of the substances if we know the delta H of the reaction and we know the formations of the other things in the reaction. So I'm going to give you a little more information this time, okay, and let's see what we're missing. All right, I want to know the delta H, the energy required of formation of H2S. H2S is a reactant in this reaction. I don't know this, okay, so that's what I'm looking for, and that's going to be in the units of kilojoules per mole. I know I'm giving you the fact that SO2 is a minus 296.8, and our buddy water, you're going to get used to this one, is 285.8. The delta H of the reaction at standard conditions, so that's the total, right, is a negative 1124 kilojoules. Okay, so how do I do that? Well, what was Hess's law? Hess told us that the total of the reaction, 298, okay, is equal to all of the products minus all the energy involved in the products, I should say, minus the reactants. Okay, see a trend? Okay, so this time I know the total, so I'm going to say a negative 1124 kilojoules is equal to the products minus the reactants. Now, what am I going to have to do before I work this problem? Yes, I'm going to have to go to Appendix K, your friend, and find out what those standard enthalpies are for these. Now, I would normally have to do that, right? Do you have to now? Well, no, because what? I gave them to you. So I've already given them to you right here. So you don't even have to look them up. Okay? Now, if I didn't give them to you, what would you do? Go to Appendix K. Okay? All right. So when you're working thermo problems, remember, you're going to have to do a change in temperature. And you're probably going to have to use Appendix K. Okay? All right, so just try to keep that in mind as you're going through these. That's your just little kernels of wisdom for this. All right, so for our products, we have 2 times minus 296.8 plus 2 times minus 285.8, right? That's all together, brackets. And then minus what? 2 times x. I just leave it as a x because it's just algebra, okay? Now, it would be plus 3 times 0, right? But remember, oxygen is elemental state, so it's 0. All right, so minus 2x. Okay, now, here's where the algebra comes in, and you got to remember this, okay? All your numbers need to be on one side of the equal sign, and all the stuff with letters needs to be on the other side. All right, so I'm going to end up with a minus 2x equal to a number over here. All right, so what you're going to find is you're going to add those two numbers together, 2 times a minus 296.8, and then added to another 2 times 285.8. So that's going to give us a total of a negative 1165.2 minus 2x. All right, now I need to take that number and get it over here with this number. Okay, and they're kilojoules. I should label that for you. Okay, when I move that to the other side of the equal sign, what happens to the sign on that? It changes, okay? It goes from a negative to a positive. So when I move it over here, it becomes positive 1165.2 minus 1124, okay, equals minus 2x. All right. So that's going to end up giving me 412 is equal to minus 2x. Or 206 equals minus x. Now, do I want a minus x? No, I don't. So if I want an x instead of a minus x, what do I have to do? Well, I can multiply by a minus 1 to both sides, or whatever how you want to look at it, okay? But if I change this sign, I change the sign on the other side of the equal. You always have to do the same thing. So this ends up algebraically being x equals minus 206 kilojoules. Now, if you wanted to change that sign way back, I would normally do that, but I didn't want to lose anybody. But x is going to equal a minus or negative 206 kilojoules. So is that one exothermic or endothermic? Well, we already knew what? That it was exothermic. Because exothermic or endothermic is based on the total of the reaction. All we were finding here was one of the components, which was the H2S. And so this is how many kilojoules we would have of the H2S. And it's actually, since these were in kilojoules per mole, should have left it at kilojoules per mole. Okay? All right, so that's how you work those. The Hess's law. It's mostly adding and subtracting. It's mostly paying attention that you don't mess your sign up, okay? And remembering your basic algebraic rules on how to go through those steps and work those problems. Okay? And that's it. That's the part 2 of this. So we're done with Hess's law and calorimetry. And I will see you back when we start doing changes in internal energy.